What if everything we thought we knew about how the universe ends is quietly falling apart, and the man who saw this kind of moment coming wasn't Einstein, but Richard Feynman? For nearly a century, Albert Einstein's mathematics has shaped our picture of the cosmos. He gave us the cosmological constant, the silent term in his equations that we now call dark energy. And for decades, cosmologists believed it was the steady, unchanging engine pulling galaxies apart forever. But over the last few years, something extraordinary has happened. 9 separate discoveries have started whispering the same impossible message. Dark energy might be dying. And if it is, the universe is heading somewhere very different from what Einstein's equations predicted. Feynman, who spent his life telling students never to trust an answer just because it was beautiful, would have loved this moment, because this is exactly the kind of crack in physics he was always pointing at. To understand why this matters, you have to go back to 1917. Einstein had just finished general relativity, the most elegant theory in physics, and he hit a problem. His own equations told him the universe should be either expanding or collapsing, but at the time everyone believed the cosmos was eternal and still. So Einstein added a small term to his equations, a kind of cosmic pressure pushing outward, and called it the cosmological constant. He used the Greek letter lambda. Years later, when Edwin Hubble showed galaxies were actually flying apart, Einstein famously called this lambda his greatest blunder, and he removed it. For decades, the cosmological constant sat in the dustbin of physics. Then, in 1998, 2 teams of astronomers studying distant exploding stars, called Type Ia supernovae, found something that shocked the world. The expansion of the universe wasn't slowing down under gravity. It was speeding up. Something was pushing space apart, and the simplest explanation was Einstein's old, abandoned constant. Lambda was back. Cosmologists gave this mysterious push a new name, dark energy. By the early 2000s, a clean, confident model had taken over physics. It was called lambda CDM, and it described a universe ruled by cold, dark matter and a perfectly steady dark energy. According to this model, dark energy would never weaken. The universe would expand forever, faster and faster, until galaxies disappeared from each other's skies in a slow, cold ending called the heat death. And here is where Feynman's voice starts to feel important. Feynman never met dark energy. He died in 1988, 10 years before it was discovered. But his entire philosophy of physics was built on a single rule. The easiest person to fool is yourself. He was deeply suspicious of theories that became too comfortable, especially when they relied on numbers nobody could explain. And dark energy is exactly that kind of number. The amount of it in the universe is so absurdly small compared to what quantum theory predicts, off by a factor of 10 to the power of 120, that physicists call it the worst prediction in the history of science. Feynman would have stared at that gap and said something has to give. He wouldn't have accepted that the universe just happens to have the right cosmic pressure by coincidence. He would have pulled the theory apart, looking for the place where our assumptions break. And remarkably, that's exactly what's happening right now. The first crack came from a project called DESI, the Dark Energy Spectroscopic Instrument. DESI maps millions of galaxies across billions of years of cosmic history, measuring how fast the universe was expanding at different ages. In 2024, its first results landed, and they were strange. Dark energy didn't look constant. It looked like it had been stronger in the past and was now slowly fading. Then in 2025, the next round of DESI data came in, and the signal got stronger, not weaker. The picture wasn't a fluke. Something about lambda was changing with time. And that is impossible in Einstein's original framework. A cosmological constant, by definition, doesn't evolve. It is the same yesterday, today, and forever. If dark energy is weakening, then it isn't really a constant at all. It is something else, something dynamic, something we don't yet have a proper name for. But here's where it gets really strange. The DESI results don't sit alone. They line up with several other puzzles cosmologists have been quietly arguing about for years. There's the Hubble tension, where measurements of the universe's expansion rate disagree depending on how you measure it. There are anomalies in the cosmic microwave background, the leftover light from the Big Bang. There are unexpected patterns in baryon acoustic oscillations, the ancient sound waves frozen into the structure of galaxies. There are strange tensions in galaxy cluster counts. Each one, on its own, could be dismissed as noise, but together they form a pattern. The standard model of cosmology is bending. Theorists have been ready for this. For years, physicists have proposed alternatives like quintessence, a kind of evolving dark energy field that can grow or shrink, and modified gravity theories that adjust Einstein's rules on the very largest scales. These ideas were once considered fringe. Now they are being taken seriously in the top journals. Think about this for a moment. If dark energy really is weakening, the future of the universe changes completely. The slow, cold heat death is no longer guaranteed. Some models suggest the universe could eventually stop accelerating. Others suggest it could even reverse, leading to a distant collapse called a big crunch. Still others point to something stranger, where the structure of space itself could become unstable. We don't know yet, and that uncertainty is exactly what Feynman would have celebrated. He once said that physics is most exciting not when we have the answer, but when we have a contradiction we can't explain. Einstein gave us the most beautiful equations of the 20th century. They still work magnificently in nearly every test we can run. But the cosmological constant he reluctantly invented, then abandoned, then accidentally resurrected, may be telling us his picture of the cosmos is incomplete. Not wrong, just unfinished. And Feynman, with his stubborn habit of questioning every assumption, gave us the mindset we need to face that. He taught generations of physicists that nature doesn't care how elegant our equations are. It only cares about what is actually true. So here we are, in 2026, watching a quiet revolution unfold. The universe isn't ending the way the textbook said. The constant isn't constant. The mathematics that felt finished is opening up again. And somewhere in the data flowing in from DESI, Euclid, the James Webb Space Telescope, and dozens of other instruments, a new picture of cosmic fate is forming. We don't know its shape yet, but it is starting to feel like the kind of mystery Feynman lived for. The kind where the answer, when it finally arrives, doesn't just rewrite a chapter of physics. It rewrites the ending of the entire book. So here's the question worth sitting with. If Einstein's most famous mistake turned out to be one of his deepest insights, what other forgotten ideas in physics might be hiding the next breakthrough? And how would Feynman, with that mischievous grin and that endless curiosity, tell us to start looking for them?